so we are on, let's do to start off with, let's do example 14-41. The air in a room has a pressure of 1 atmosphere, a dry bulb temperature of 24 degrees Celsius, and a wet bulb temperature of 17 degrees Celsius. Using the psychrometric chart, determine A, the specific humidity, B, the enthalpy in kilojoules per kilogram dry air, C, the relative humidity, D, the dew point temperature, and E, the specific volume of the air in meters cubed per kilogram dry air. All right, so we have given is a pressure of 1 atmosphere, okay, and so that's 101.325 kPa, and that lets us, use the chart, the psychrometric chart, okay, because it's the chart's 1 atmosphere, and if we're at least close to 1 atmosphere, we can assume we're at 1 atmosphere and still use the chart. Okay. All right, so they gave us a dry bulb temperature, which is just typical temperature, but dry bulb, which is typical temperature, which is 24 degrees Celsius. All right, they gave us a wet bulb temperature, which is 17 degrees Celsius. And they told us to find a whole bunch of stuff. Find stuff. Yeah. We're going to find, using the psychrometric chart, we have to find a specific humidity, okay, B, enthalpy, and that's kilojoules per kilogram dry air. C, relative humidity. D, dew point temperature. And E, specific volume. Of the air. Okay. And that's in meters cubed per kilogram dry air. All right, our schematic. Come on, there we go. Again, our pressure is 1 atmosphere or close to 1 atmosphere, so we can use the chart. Okay. The other thing is we have dry bulb and wet bulb. Okay, so dry bulb, we said it was 24 degrees Celsius, and wet bulb was 17. Well, that's enough on this chart, and we'll see that in a second, to draw a point, okay? This makes basically two lines intersect into a point, having those two properties. So that would fix our state, okay, for humidity. So we can get all from these two things, all these other properties above, okay? All right, so let's go to the chart. Okay, so we have 24 for our dry bulb. So let's draw that. Oops. Let's try that again. All right, so dry bulb's down here at the bottom. And we got 24 right there. Okay. So that's our 24 degrees Celsius line, straight up. Okay, so our horizontal line. And then we got 17 degrees Celsius wet bulb. Okay, so we see wet bulb being labeled right here with those little dotted lines for 25. So we keep moving. Here's 15 over here. Now we need 16, 17 is the one right above it, two lines above it. Okay, so let's, that would be 16 right there. Oops. It's one more above that. Right. So 15, 16, 17 right there. Okay, so that's our wet bulb is 17 degrees Celsius.
Professor, is that the correct line for 17 degrees Celsius?
Yeah, we got 16 right here. Right, and then this would be, or that's 15, and this would be 16, and then that would be 17.
Okay.
Yeah.
Okay, thank you.
Yep. Yeah, the wet bulb's tough to see, those little dotted lines.
Okay, just out of curiosity as well, should we follow the dotted lines instead of the only reason I asked that question is because when I look to the left where it says saturation temperature, the 15 is on, like, cutting off that line, so I thought that one was 15.
Yeah, it would be, this one's 15, right? So then this one would be 16, yeah, 17.
Okay, thank you.
Yeah. Yeah, it's the dotted lines, the solid lines are enthalpy. They're close, but a little bit different, right? Okay, so we have.
I'll do that too. It's okay.
All right, so then our point is right here, right? So now we have our state. So that is where we are on the psychrometric chart. So now we can start pulling other lines from that, okay? So all we need is two things on this chart, and we get all the others, okay? So we have to get, first they asked for specific humidity, so that's over here, okay? So that's our horizontal lines, okay? So let's draw some, see if it'll allow me to change the color here. Let's do gold, okay? It might not. All right, so if we draw a line across, now we have where we are for the specific humidity. So we get, see it here, we see 8 right there. All right, and there's 10 up here, so 9 would be the second line in between, so we're like half. So this looks like maybe 0.095. and that's kilogram vapor per kilogram dry air. So it says 9 because this is grams per kilogram. Okay, so converting it to kilogram, we have about 0.095. So you don't have to get hung up on, you know, that third decimal place or far accuracy on the chart. That's just close enough when you're reading it. Okay. All right, so that's our specific humidity. Next is enthalpy. Okay, enthalpy is lines that are close in slope to these wet ball, but they're a little bit different. We have enthalpy labeled over here. Okay, so our slope is across there. Okay, and we got to go through our lines. So see how they're close in slope, but not exactly, right? So in this line, you can see they're labeled right here for, let me make that a little bigger, that circle. Right, so there's 50, and then we're at 48 over here. Same thing when you look at what you got right here. 50's late. Let me make that a little bigger again. 50 is labeled on the line that comes across, and then 2 slashes out. And so we're at about, you know, enthalpy of 48 kilojoules per kilogram dry air. Okay. And next is humidity, relative humidity, right? We already did specific humidity, which is the horizontal line. So relative humidity, we look for our labels. So here's the label of 10%. So it's these curved lines. Okay, ours looks very close, you know, to the 50% relative humidity line. So that's close enough to just say we're at the 50%. Okay. Then we have dew point temperature. So this is the only one that's not directly labeled on the chart. It's there, but it's not directly labeled. Okay, so we got to think about what dew point is, and that's if we cool this moist air at the same partial pressure of the water vapor till it hits the dome, then it'll start condensing out, having the dew. So what that is taking the same specific humidity and cooling it until it hits basically 100% relative humidity. So it's this point right here. Okay. So right where it hits right here, because that's the 100% relative humidity line, we just cooled it. We took our point, we cooled it all the way until it hit that 100% relative humidity by keeping the specific humidity, the horizontal line. Okay, so that means our point is, if we want to read temperature for that new point of dew, where the dew point is, it's right here. Okay, so that looks like dew point is 12.5 degrees Celsius. Okay, any questions on that one? Basically, we took our point and went this way, right, until we hit that 100% relative humidity curve. Okay. All right, so that's our dew point. Now we got, last is specific volume. Okay, so labeled right here of 0.2 or 0.92. So we work our way. Here's 0.9, 0.88, 0.86. Although it's not tough. It's tough to see. It's underneath our line. Here's 0.84. That means we got 0.85 right there. And our line, let's do it. If we draw a slope line through it, it's something like that, you know, somewhere in there. It's tough to get our point now, but that's where we are. And that's good enough to say it's about 55.8, because since this is 8.5 right here, this is 8.6, so I'll say I'm halfway in between. And that's meters cubed per kilogram dry air. Okay. Any questions on that? All right, so we'll rewrite from these two things, just knowing dry bulb, wet bulb, right? We were able to get our specific humidity, our enthalpy, which is, this is the enthalpy of the moist air, even though it's per kilogram of dry air, the kilojoules already includes the enthalpy, the sensible enthalpy from the air and the latent energy from the water. Okay, relative, we got 50%. Dew point, we got 12.5 degrees Celsius. And specific volume, we got 0.855 meters cubed per kilogram dry air. So two properties got us all the others, or we could have some of these other properties on the right, one or two of those, as long as we have two, it fixes our state, we can get all the other ones. Okay, so that becomes very important. All right, let's do another example. Let's do 14-68. Air enters a 30-centimeter diameter cooling section at 1 atmosphere, 35 degrees Celsius, and 45% relative humidity at 18 meters per second. Heat is removed from the air at a rate of 750 kilojoules per minute. Determine A, the exit temperature, B, the exit relative humidity of the air, and C, the exit velocity. Okay, so we have a diameter of 0.3 meters. We have a pressure is 1 atmosphere, right? So it says that means we can use the chart, right? We have a temperature at the inlet, which is our dry bulb of 35 degrees Celsius. We have a relative humidity of 45% at the inlet. We have a velocity of 18 meters per second and a rate of heat transfer 750 kilojoules per minute. Okay. They want us to find the exit temperature. So that's T2. The exit relative humidity. And the exit velocity. Okay.
Why did we assume that the inlet temperature was the dry bulb?
So anytime regular temperature that you say temperature, it's dry bulb. So all the temperatures we've used in all the problems previously, when they just say temperature is 20 degrees Celsius, temperature is 300 Celsius, that is the dry bulb temperature.
Okay.
All right, so we have our section of duct. Comes in, state 1, leaves at state 2. We have some cooling section going on here where it's removing heat. So maybe this is removing heat from the air, but putting it into refrigerant, let's say, in that section in the vapor compression cycle. This could be that section where we're putting heat into it, right? It's removing it from the air, but going into that coil, okay? Okay, so assumptions, it's steady state. We're always going to have, in some of the equations we even use, it already assumes steady state in them for this chapter. Okay. All right, so based upon, let's start here. What I mentioned about properties in the last problem, do we have enough for state one to fix our point on the psychrometric chart?
We have the dry bulb and the relative humidity.
Yep. So that's basically right here is enough to fix that inlet. So to get all the properties we would need for state one, we have two things. So we can draw our lines and see where they intersect and get our point. Okay. But on the outlet state, do we have anything right now? I don't see anything, right? So let's at least start. Let's start there. So we have state one. We have a dry bulb of 35. We have a relative humidity of 45%. And then we know we can get anything we want there. State two, we don't have anything yet. Okay. But we're going to be asked for exit temperature, relative humidity. So those are properties, whether we get those directly or get a different property and use our state to understand. Okay. So this is all from psychrometric chart. Spell that. Chart. So that's figure A dash 30, 31. Okay. All right. So we have at least a setup there. What do you think we want to do next?
Should we figure out the enthalpy of state one and then use open system, try to figure out H2?
Okay. So if we enthalpy state one, I'm going to show the psychrometric chart at the end, just because I don't want to keep flipping back and forth. So I'll show you. We'll go through the problem on the psychrometric chart afterwards. But yes, we can get enthalpy one. Okay. Which I have 76 kilojoules per kilogram dry air. And then you said open system to figure out something at state two. Okay. So if we look at, let's see, COE open system. I already said it's steady state, right? We'll neglect kinetic and potential. There's no work in our schematic. Okay, so I have this so far. What do we do next? I have basically the mass flow to dry air carrying enthalpy in, the mass flow to dry air carrying enthalpy out. Let's bring in our conservation of mass. Okay, so this is where, from the lecture, we saw we split this up. Okay, we have in the conservation of mass, we have the dry air section. And see it already in the equations you see in the book, it already has steady state, right? You don't even see the dm dt because it's already assuming steady state. And if we set this up, we see dry air is there's an amount of dry air entering at 1, same amount of mass flow rate of dry air is leaving at 2. Okay, so it's just the mass of dry air, mass flow rate of dry air. And then we do our water vapor. Okay, so if we look at our diagram, we have some water vapor that's coming in with the dry air at 1. We have some water vapor that's leaving at 2, right? There's no other water leaving anywhere or being added, right? So we have water vapor at 1, mass flow rate of water vapor at 2. And this is where we brought in the lecture, the specific humidity, right? If we rearrange this, we have this. So rearranging for mass of vapor, we have this. So we can just make this dots, and we see now we can relate what the mass flow rate of water vapor is to the mass flow rate of dry air times the specific humidity. So we can put that in for here and for here, okay? So then that just becomes so what does that simplify to then?
Mass A times W1 minus W2. Oh, other way around.
Well, no, so no, these can't. The mass flow rate of air is the same.
Oh,
right?
true. So they cancel out.
Yeah. So then we just have the specific humidity is the same. Okay. Which we come back up here, and that's one of these properties. So we have for state 2 something that tells us. Okay, so if we go and grab the specific humidity at state 1, now we have the specific, basically it's the same. So we have one property for state 2 now. We need another, and you said We're still working towards that enthalpy. Okay, so we have enough to simplify our conservation energy. So we went through the conservation of mass, go back to this conservation energy, and we can put the mass flow rates together, right? Or, I'll just leave it without that because we said we're going to solve it for H2, right? All right, so we have enthalpy 1. We already looked that up. We were given in the problem the rate of heat transfer, okay? So that means we still need to figure out the mass flow rate of dry air, okay? How do we do that? Any ideas?
Using the conservation of mass, can we say what I think this is where like I got confused. We have
conservation mass here, but we can use the mass flow rate equation. If that's what you mean. So mass flow rate, okay, and that's where mass flow rate is density, velocity times area, okay. And in this one, property in the psychrometric chart is specific volume, so we have velocity area over specific volume, okay. All right, so velocity, area, specific volume, do we have enough information to get that?
for state 1, I think.
Yeah, state 1, we got a velocity, right? And we got a diameter. All right, and then we just got to look up specific volume. Okay. All right, so we'll make this all 1. So now we have everything. We have velocity at inlet. We have the diameter of the duct, and we looked up the specific volume. Okay, so we plug that all in, and we get 1.422 kilograms per second. So now that's everything there. Okay, so for the conservation energy other than H2, so we can solve for enthalpy at the outlet, and we get 67.21 kilojoules per kilogram dry air. Okay, so we have H2. So the other thing I want to just point out again in these, as I mentioned in the lecture notes, this is kilogram per dry air, right? So that means that's why we only had to worry about the mass flow to dry air in the conservation energy. But inside the enthalpy includes dry air and the water vapor portion. Okay, we derived that in the lecture. Okay, even though it's per kilogram of dry air, the kilojoules includes that water vapor, okay, in it. Okay, so there's no Cp delta T we can put there because it also has inside this enthalpy is the the dry air portion, which is Cp delta T, but also the latent energy from the water is included in that. Okay, even on the psychrometric chart, it includes that. Okay. All right, so we have H2. So our state is fixed, so we can get everything at the outlet, outlet state from these two things. So exit temperature and exit relative humidity are just two properties. So if we have these two, we can already get P2. And I'll show it on the psychrometric chart in a minute. So we get 26 and relative humidity is 74%. Okay, and then the last thing we have to solve is the exit velocity. How do we do that? Any ideas?
A mass flow rate, then maybe that.
Yeah,
So
yep. So the mass flow rate of dry air is the same at the inlet to the outlet, right? So then we can just relate it. We can either just solve this directly, where we have mass flow rate of air at the outlet, right? It's just the mass flow rate of air, but we make this V2 pi over 4 d squared specific volume at the outlet, okay? So we have the mass flow rate of dry air, it's the same, right? We're looking for velocity, diameter of the tube is the same. Now we just need to get our specific volume at the outlet. So from our psychrometric chart, see if I can find where I have it. Okay. .869 around. All right, so if we got that, all right, so then the only unknown is velocity 2. So we solve and we get 17.5 meters per second. Okay. Any questions? All right, so let's do the psychrometric chart. All right, so we have at first state, we have 35 degrees Celsius. Okay, so that's here's 30, 40 at the bottom. Here's our 35. So that's our dry bulb, 35 degrees Celsius. Then we have relative humidity of 45%. So it's right in between. Right about there is 45%. Because here's 40, here's 50. Okay, so let's see if I can make a better line here. Okay. So there's our point. Okay. So then from that, our process was the specific humidity stayed the same, which is our horizontal line right here. I said it was 0.16, so right about there. .016 kilogram vapor per kilogram dry air. And we're cooling, so we're going to the left, right, from our point. Right, if we were heating, we would have gone to the right from our point, but we're cooling. And the other thing we knew from the conservation energy was enthalpy, which we said was 67.21. Well, we can maybe get 67 in a little bit. Okay, so here's 60, here's 70, so we're going to go a few slashes below, maybe right there. Okay. And there's our point right there. So we went basically from point 1, our state 1 right here, to our state 2 right here. Okay. And then we needed our exit temperature off of that, which was down here. It's our 26 degrees Celsius. We had relative humidity, right, between the 70 and 80. So it's about a 75%. See, our specific humidity stayed the same, right? We were right along this horizontal line. But our relative humidity changed, right? Because the amount of moisture that the air can change changes with temperature. And we cooled, we went to 26. So we dropped in temperature, so the air can't hold as much. So we have a humidity of 75%, relative humidity. Okay. What else did we have to find? We did enthalpy. Okay, at the H1, where we got about 76. Okay. We had to get specific volumes at the inlet and outlet. Okay, so that's our steep slope lines here. Okay, so there would be our specific volume for state 1, which you got about 0.895, since here's 0.88, here would be 0.89, so it looks like it's kind of in the middle. So you have 0.895. Okay, and then we had to do that for the outlet state, right? Okay, in our outlet state, we ended up having, I mean, I wrote down 0.869, but it could have been 0.87, right? Because you have 0.86 here, 0.88, and we're kind of right in between, but any of that's close enough. Okay. Any questions?
So what's the highest value like specific humidity can be?
What the specific humidity can be. So on the chart, it shows like 30 here.
Is that like is that like the highest then? 30?
I'm not sure. That's a good question. I'm not sure actually. I think in HVAC problems, this is usually, I mean, your range of temperatures that you're going to have is here because this is 50 degrees Celsius. So I think you can still get more than that. I think they're just, their ranges, they leave it there in typical HVAC problems. Okay, since this being 50 degrees Celsius, which is, pretty warm, of, the range then of what you have here.
Is this the only chart that we're going to use? Or are there like multiple for different pressures?
No, it's the only one. I mean, there are smart like software out there that'll generate new charts for different pressures, but you have to use equations if it's way off, which I don't really go through all that because the equations for every single one of these would take a long time on a test, right? Because all these properties have an equation to it, and it takes considerable amount of time. So we're going to be able to assume that we're near 1 atmosphere. Okay, even if it was slightly off, let's say 100 kPa, that's such a small pressure change that you can still assume it's 1 atmosphere. Okay. Any other questions? Okay, the other thing I wanted to say is the example we kind of did in the cooling in the lecture notes. It went. Let's change the color here for this part. Okay, it went, and if it hits this dome, right, if it hits this, not dome, but this 100% relative humidity, you can't go past it. So that's when water starts dropping out. So in our problem, we didn't get to the 100% relative humidity, but if we cooled enough to hit there and kept cooling, right, kept dropping our temperature, we only went to 26, but if we went kind of beyond this 21, we would have started condensing water. Right? As you move along here, you're condensing water, right? You have a point here. Now your exit state has a different specific humidity way over here or way over here. And you're dropping out water because your specific humidity is changing, right? So that means there's water leaving your boundary.
And why did we assume again that it was cooling?
It told us.
Oh, okay.
It was a cooling section, so it was removing 750 kilojoules per minute. Okay. Yeah, if we were heating, we would be going to the right from our initial point. Okay. Any other questions? All right, let's do another problem. Let's do 14-72. Okay, so 14-72. Air at 1 atmosphere, 15 degrees Celsius, and 60% relative humidity is first heated to 20 degrees Celsius in a heating section and then humidified by introducing water vapor. The air leaves the humidifying section at 25 degrees Celsius, 65% relative humidity. Determine A, the amount of steam added to the air, B, the amount of heat transfer to the air in the heating section. Okay. So we're given pressure, it's 1 atmosphere. So we have chart. We have temperature 1, again, is our dry bulb, is 15 degrees Celsius. We have relative humidity at 1, 60%. Exiting the heating section is a temperature of 20 degrees Celsius. And then exiting the humidifying section is 25 degrees Celsius and a relative humidity 65%. Okay. They want us to find the part A is the amount of steam added to the air. Amount of steam added to air. And that ends up being that we'll see, how to label this. Maybe we don't have a variable until we start solving it, but it'll end up being the change in specific humidity. But we'll see that when we solve. And then part B is the heat transfer to the air in the heating section. Heat transfer, and that's the heating section. And that'll end up being lowercase q. And again, we'll see that when we solve. All right, schematic. All right, we have a section here. Okay, and we have one entering. Now we have the heating section. Okay. So this coil is now basically adding heat. And then we exit that. That's our state 2. And we have our spray section we're adding. This is where we're adding water. And then we exit at state 3. Okay, so we have a heating section and then a humidifying section. Right, steady state. Collect kinetic potential energy. All right. What do we see with the properties that we're given in our givens? Do we have enough information for state 1 to find a point on the chart?
Yeah, we have the dry bulb and the relative humidity.
Yeah. Okay. How about state 2?
Nope.
Not
State
yet, right?
state 3 we do.
Yeah. Okay. Okay. So that's our key on our states, and that's kind of key when we think about what we're going to analyze too. And that's what kind of changes from one problem to another, because they'll give you some information about state 1 in this one, but we don't have as much about state 2. Or maybe a different problem, they don't give you as much about 3, or but give you more about 2, or just try to move around what you know and what you don't know. Okay, but we have state 1, we have a dry bulb and a relative humidity, right? So we can get anything we want from the chart then, properties wise. State 2, we just have a temperature for right now. So we need to figure something out there. And then state 3, we have our dry bulb. Let me put the dry bulb here, dB, as a reminder. and then relative humidity. So we can get anything our heart desires, right, for state 3's property. Okay, so where do we want to start? Dan. So we used everything basically in our givens, right? We said pressure is 1 atmosphere, so we can use the chart. We have everything then from here. So now it's looking at our schematics. What do we want to do?
Conservation of mass.
Okay.
Determine.
All right, so conservation of mass, right? We have a section 1 to 2, 2 to 3, or we could even analyze it if we wanted to all the way from 1 to 3, but we'll leave it 2 separate sections. Okay, so we said conservation of mass, and we'll see what comes out of that. Okay. So we have dry air. Is the mass flow rate of dry air changing throughout this whole thing?
Well,
No. Dry air, the amount of dry air at 1 is going to still be there at 2. Same mass flow rate of dry air at 3, right? We're not adding in dry air, removing dry air, so the mass flow rate of dry air stays the same. So at 1, equals 2, equals 3, which we'll just call that mass flow rate of dry air, just subscript A. All right, now if we look at water vapor, or water, all right, so if we start off with section 1 to 2, we see water vapors being, because it's moist air at 1, so there's some water vapor there. Okay, we're not changing anything with the water vapor through 1 to 2, right? So the same amount is going to exit, right? If we put in our specific humidity, then this just becomes dry air at 1, specific humidity at 1, dry air at 2, specific humidity at 2, and the same cancellation we saw above, the mass flow rates are the same. So our specific humidity is the same. Okay. And that's important, right? Just like in the last problem, that means we have our second property for state 2. So now we can really get anything we want that we need. All right, so if we do 2 to 3, for the mass, for the water vapor conservation of mass. So now we see we have water vapor coming in at 2 because it's moist air, so there's some water vapor there. But now we have some water entering our boundary from the spray, right? That's crossing our boundary. And then all of it is exiting here at 3. Okay. So we have a 1 entering. We have that water that we're injecting, and then that all, oh, that should be 2. And then that all exits at 3, right? So if again, for the moist air, if we put in our specific humidity now, rearrange. We know that these are the same. Okay. The mass flow rate of dry air is the same, 2 and 3. Okay, and that would tell us the mass flow rate of water injected. The one thing, and that's like I said in the beginning when we were doing the givens and the fines, is the mass flow rate of water injected. It's asking the amount of steam, say, the amount of steam added to the air. Well, we don't have mass flow rate of air, and they didn't give us anything with velocity or mass flow rate of air. So we don't know the mass flow rate of air in the end from 1. So it's more of a divided out kind of problem. So, which isn't exceptionally clear. But we divide it out, and that's, you know, our amount of water we have to inject, you know, and the mass flow rate of dry air is just our scalar. Okay. All right, so specific humidity 3 and 2, we need to just grab those from the chart, and we'll do that, the chart in a second, but we can, at 2, we can just write it down for now. And 3. Okay. And if we plug those in and solve, we get the difference, 0.007. Any questions on that? Okay, so that was part A.
Does the relative humidity change at state 2?
Yeah, from 1 to 2, the relative, yeah. Yep, relative humidity is basically always changing. So if we're changing temperature, which is 15 to 20, we're changing relative humidity. It's the specific humidity where the processes can stay the same. Okay. All right, so part B, the heat transfer in the heating section. What do we do for that? How do we get the heat transfer in the heating section?
Conservation energy?
Yeah, so conservation energy, and we only have to do 1 to 2. Okay. steady state. Like connect potential. There's no work. All right. All right, so similar simplification as the last problem. We have the air is the same, mass rate of air. Moving things around, dividing by our mass flow rate of dry air. It's just the change in enthalpy from 1 to 2. It means we need our enthalpies. This was the same. Specific volumes or specific humidity here. Right, enthalpy at 1. Enthalpy at 2. So therefore we get 4.5 kilojoules per kilogram dry air. Questions on that? I'll show this, the psychrometric chart, but right before that, I want to say is we didn't end up having to do the COE because we solved for the second part, heat in. We didn't end up having to do a COE for 2 to 3, and that's because of what we were given. Okay, so, but if we didn't know as much on the outlet state at 3, but we knew more information, let's say at 2 or something like that, we could use conservation energy from 2 to 3. We would just need to know the temperature of the water we're injecting. Like we would have a temperature here, we would have given, and that would allow us to get what that enthalpy is, because that would just be the HF in our table at that temperature. Okay, so let's just call this the temperature of the water if it was given. Then we could look up HF, and that would be the energy is this mass flow rate times this that's being put into our boundary from the water. All right, so let's do our chart. All right, so state 1, we have 15 degrees Celsius. So we have this vertical line. All right. And then we had 60% relative humidity. Right? So here's the 60% line. So right there. Okay, so there's our state 1. Okay. Now 1 to 2, where specific humidity is being held constant. Okay. So it's a little different than what I had, 15 and 60. That's right. And we hold constant, and then we hit 20, right? On our okay, so that's our temperature equal to 15. Here's temperature equal to 20. And our second point. Okay, so we went right like that. Okay. So that's our heating section. Okay. Then we have our where we humidify, right? And we had 25 degrees Celsius is our dry bulb. Okay, so that's right. So there's where 25 ends up. This is 25 dry bulb, right? And 65% relative humidity. So we have our 60, 65 is right in between, 70, 60s. So we're right about there. So for our point, so when we're injecting, we're going from 2 to 3. Okay. And then we pulled enthalpy for each of these, right? Oh, and we specific humidity. So right about there. Okay, so that's where I had 13.013. And then down here I had 0.6, but when I drew it this time, it's a little different. So you could have what I have on this chart. That's fine. So here I have 0.65.
When we're going from state 2 to 3, is
Yeah.
that a linear change or is it actually like curved a bit? Or does it not
It's
even
not,
matter?
it would be a straight line. I mean, or dash line. It doesn't necessarily matter too much how we know it's going from 2 to 3. But yeah, I mean, I don't know whether it curves or has a slight curve to it or not.
It's just the properties is what's mainly important.
Yeah, yeah.
Okay.
Mm-hmm. All right, so we have specific humidity that we grabbed, right, from our points over here and here. And then the other one was enthalpy, which is just our lines right here. Okay, so I have at H3, I had 58.5 kilojoules per kilogram dry air. 2, right around there, which was 36.5. And last one is there, which is 32. or it could be moved a little lower. And that would be fine too. Okay. Any questions?
Can you show the last chart that we did for the last problem?
This one? I have a lot of extra lines on it, but yeah.
I was just screenshotting it, look at it later.
Okay. Yeah, we see in this one, we go from 1 to 2, we go from right to left because we're cooling, right? And then if we kept cooling, we would have dropped out some water, you know, and had our specific humidity somewhere around here. In this one, we're heating, right? So we went from left to right, okay? We went this way, and then we humidified, so we jumped up in specific. Right, so we jumped up in our specific humidity because we added water, right? Okay, any other questions? And that's it for today. Oh, go ahead.
Real quick. So how does this specific humidity not really change, even though we're adding a heat source in it?
Because specific humidity and relative humidity are two different things. So relative humidity changes. That's these lines. Okay, so relative humidity changed from that to that, right? It changed. Specific humidity is just the ratio of mass of vapor over mass of air. And if you add heat, you're not changing mass. You're just changing energy, right?
Thanks. That makes sense.
Yeah, so those stay the same. That's why specific humidities, the better quantity in the math part, the engineering part, but relative humidity is better because that's where we know what people like, right? We know what in HVAC, you know, people like around 60%, you know, 40 to 60% relative humidity to feel comfortable. So that's where relative humidity comes into play. But it changes with temperature. Anytime temperature changes, your relative humidity is going to change.
Thanks for clearing that up.
Yep, that's a very common mistake, is getting those two confused. Okay, well, and that's it. Unless there's any other questions. And I'll see you guys on Wednesday.